Okay, hello class, weekly update 4. Okay, a couple announcements, and then we'll talk a little bit about the homework. So quiz work, again, great job on that. Keep submitting so I can, if there's any discrepancy, or I can use that to sort of up your grade if you're having lower quiz grades, but you're doing a lot of work. And I can go look at that too if it was just like a entry error. Some ones that are really good. So if you are struggling on some of those textbook writing questions, I think work by Chloe, Zach, and May are really good to contact your classmates. And Zach always Tex is up, so he does them in LaTeX. If you're not familiar with that, that's something as a grad student you're going to want to, or thinking about grad school. Some of you are in 451, but thinking about grad school, it's something you want to learn slowly as you go through your curriculum here. And a great lifeline is to Zach because he's got the files and templates. So when I was in grad school and started learning it, there weren't as many resources online. There was one bootleg paper copy of like a 90-page manuscript of how to learn LaTeX, and we had it in the grad student office, and it was always there, and you grab it when you were stuck. And now you can pretty much just Google things on command. How do I typeset for the gradient in LaTeX? And just Google that, and boom, you'll see. But setting up that first file, you might ask Zach if you could borrow his quiz 1 homework, and then you're just gonna, that's a great example, and then you'll figure out it's already shows the headers and tail of the file that you need, because it's kind of like a little bit of a programming language, but once you get used to it, you'll love tech. And another tool that you guys might like as group members, since we're doing this in this remote learning environment, is Overleaf. And if you haven't heard of Overleaf, check it out. It's basically like a Google Doc for your team, but it does it in LaTeX. So you're able to check your homework, all of you working together, like on one of the group assignments. Zach could be working on this. I could be typing if I'm on his team. I'm also typing live at the same time, and it's not overwriting anything. It's a really wonderful team tool for LaTeX. I use it all the time with for my research papers. Okay, let's see, next thing. We talked about the practice exam and the exam, how they're similar and different. If you weren't able to make the class, optional class on Monday, please check out the recording that's posted in the exam section, exam number 1. There's 2 things there. There's a practice exam, and then it shows the recording that we made. And then the next section is the exam, which is Monday. We'll be taking that during our class time with our Zoom videos on. Okay, thank you for your MATLAB assignments this week, and I appreciate also the comments that you write when you submit files sometimes. Some of you do that. That's helpful for me to see any issues or just thoughts that you had while you're doing that assignment. Some ones that were shout outs for folks that did a really nice job. Ashley or Brianna seems to know MATLAB or has some experience. So during the semester, that's a lifeline. Maddox is a great programmer. You got to see that. And Jenna did a really nice job. So those are folks, again, that might be able to help as we proceed, because we'll be using more MATLAB. But for this Monday, for our exam, remember the main thing that you need from MATLAB is to be able to take a mathematical model and use linprog and pull off what is the A, B, F, A, Q, all those parameters, just be able to pull them off. Jenna made some really good points in hers. I remember she talked about it's easy to make errors. Like you see a model that you've written by hand, but you have to remember MATLAB needs it in a very specific standard MATLAB form. And so if you had a greater than inequality and a less than inequality, you need to turn them all into the way MATLAB likes it, which I think it's less than. So some of those greater thans have to be turned in. You have to negate everything along that row and the B, right? So it's easy to forget different pieces of that when you have to add negative signs and flip things around. Same thing, another place that's easy to forget is the min or the max. I think MATLAB, I can't remember off the top of my head, but I think it likes min. And so if you had a maximization problem, you need to negate the F vector that you're putting in. And often you don't do that. You go ahead and run it, and then you're getting answers that don't quite make sense, or it's saying it's infeasible or it's unbounded or something. You know it shouldn't be those. That's your clue that it's probably an entry error. Okay, So thank you, Janet, for that reminder. All right, now let's talk about your theory homework. So I've graded these, and I won't send those out until after exam 1. I'll send you another revised line from my spreadsheet for each of you, but I did put it in the spreadsheet. Mostly nice job, lots of A's and B's, a few C's. And I put the solutions, my version of the solution, which was a proof by contradiction. We'll talk a little bit about that. That's in Oaks, so you can check it out. But I want to talk about some common themes from the homework and some shout outs for folks. So some people talked about sort of a calculus approach to this one, where they would find CPs basically. Now think about in Calc 3, when you learn that, that was always for an unconstrained problem. You would say, okay, if I have unconstrained minimization or unconstrained maximization, I'm going to go find the CPs because they're good places to look for extrema. And that strategy does help. Like there's facets of that that will help us. And if we have time this semester and get to nonlinear programming, we would see some of that. But let's just talk about the downfalls for this particular assignment. So CPs, though, that's unconstrained. And we clearly had a constrained problem here. It was a constrained minimization, I think, right? So then let's think back to Calc 3. How did we deal with constraints then? Hopefully in your Calc 3 class, you got to Lagrange multipliers. So if there was a, minimize some f of x, y, and there was one constraint, we could add a Lagrange multiplier. If there's a second constraint, we could add another one. But if you had anything beyond that, and even those were difficult just to do for an R3 problem, and now we had an Rn, and we had m constraints. So Lagrange multipliers do help us in optimization. There's a whole technique called Lagrangian relaxation of a problem. Probably won't have time to get to that this semester, but it's nice to know it exists. It is a bit of an extension of stuff from Calc 3, but just to show you the limitation of the calculus approach. So even though you could compute CPs for this, it's not going to get you to your end result for this theory problem. Another thing, a couple common mistakes is you had to also check, remember in our setup, we're always checking feasibility and optimality. So first you have to check the relationship between the two problems A and B. If I picked some solution that was feasible in A, is it also feasible in B? That was easy to check because the feasible region was exactly the same. So feasibility was an issue, but you had to write that in your proof, right? You had to at least mention that you knew any solution, including an optimal from A, would also be feasible for B. Okay, and then another approach to this, and I liked what May did here. If you're not sure which way because this was just posed, you have to decide and make a claim and then prove it. Does the claim go in this direction or go in that direction? One way to do that is to do a bunch of examples. Now you could have done those examples in R2 by hand, in R3 maybe even by hand. You could have picked a bunch of problems and just written them out algebraically and then thrown them into MATLAB's LinProg and just tried like 10 of these until you get a sense for, okay, I think it must be this way. I think that's a true statement. And now I'm going to try to work to prove that. So doing examples till you can get there. Most people fell on the right side. There's only a few of you that didn't realize this was a true statement. And so those examples give you intuition which way you want to go with this conjecture, and then you try to prove it. But I thought an interesting little twist on that was May talked about she didn't use MATLAB to generate a bunch of examples and test them with LinProg. She said, well, let me look at the LinProg. So if this was an LP, if F and G and all those things were linear, let me go ahead and think about, well, then I do require LinProg. But MATLAB asks for just the coefficients of the x's. It doesn't say anything about there being a constant, right? Because if the objective function was x1 plus 2x2 plus 3x3 plus 4, it doesn't say anything about how do you enter that plus 4. She's like, if I can't even enter it, then it must not really matter. So that was her, again, evidence or more support on the side of this must be a true statement. So I'm going to work to prove it. Yeah, that was a clever way to get at which which side you were falling on. Okay, again, you could have drawn some pictures in R2. So at Monday's optional class, you guys were doing a bunch by hand to answer our practice exam problems. Ashley had some nice ones where she drew in R2. So we just have some sort of polygon in R2. So that's it. That's the case where, okay, let me simplify this. Let me think in the easiest possible case. I have a linear feasible region, so I have a polygon. I have linear objectives, so I just have contours coming through. Right, okay, so that's the problem A, and then you do the same thing for problem B. The feasible region is exactly the same polygon. The only thing is changing, the contours are exactly the same. The only thing that's changing is the level, the labels on those, the Z equals K labels, they increment by K, right? So that would have helped you get there. That's obviously not a proof because it only works in R2. Sure, you could have extended that to R3 and say, okay, let me just visualize a polytope in R3, and I've got planes coming through it. And then same thing for the B, it's the exact same polytope. I've got planes coming through. The only thing that changes is the labels on those planes coming through. Again, not a proof, but that's the way that gets you the intuition. And then you go back to the R2 case and you say, okay, let me not make it a linear feasible region. Let's assume it's got some linear sides and then a curve or something. It doesn't even have to be convex. And then I have a linear contours, or I have nonlinear contours coming through. And you see you get the same conclusion, so that it doesn't rely on the linearity or nonlinearity or convexity of the region or the objective function. So all building up intuition, but that's not a proof yet again. And so some proofs that I liked, Ashley and Michael did a nice job, and Brianna and Jenna. And so I actually want to pull up one of these. Let me see if I can share the screen to get to. Oh yes, so let's try, maybe I like Ashley's and Jenna's. I want to put up some nice tight ones, so Brianna and Michael had some nice ones. And just an issue of time, I think I'm gonna go to Jenna's because I thought there's some pieces of thought process. Okay, what makes a good proof? Well, that's a debate, right? So mathematicians like to be sort of elitist about their proofs, and like if it's the smaller, most compressed, then they're sort of proud of it. But what makes a good proof is really often people say when it reveals the thinking, like the thought process of the person that got there, and when one statement follows another in this chain of like each time you should say, I remember Yoshi Yamamoto, he's in his late 70s, and I met him maybe 10, 15 years ago. He came to Charleston for a month to visit, and I went over there and we continued doing research. But he talks about, he's just like this optimization guru. He's written several books, but they're in Japanese. I can't read it yet. But he talks about what makes a good proof is as you go from one line to the next, you always say, of course, of course, of course, each time. And this is how I felt when I was reading through Jenna's. Now, Jenna's never had a proof writing class, and this was a very different approach to doing it. Many of you who have proof writing class know that there's some techniques or sort of tricks or tools to writing, of which I did one that's sort of a classic one, proof by contradiction, which made for a very short proof, but I don't think it's nearly as revealing of what this actually means. So Jenna talks about the two problems. And so her initial thoughts here, she's like, well, f of b is just like a linear transformation or translation. The constraints are exactly the same, so the feasible regions are the same, so she doesn't have to think about that. That's a key part. The contours, though, have the same shape, they're just shifted by k. Okay, so she's starting to see this geometrically. Let's see, and then she says, obviously this would be true graphically, but the ideas would still be valid for Rn. Great, but now she's got to actually prove that. And she's like, at a particular point x star, you evaluate the objective function, you're getting f of a x star, and same thing for f of b. And so they are just shifted by k. And so then this is also what I believed I liked about Ashley's proof too. She was like, okay, what do I know? So then she starts to say some things that we know. If X star is in the feasible region, it's in a feasible region for both of them because they have the same region and constraints. Therefore, f of b is a possible objective value, right? And then she breaks down cases, which was interesting. Another great proof technique. So even though you haven't had this class, like that is an excellent way to do things. Can you break it into cases? And so she says, what if k is 0? Okay, well then easy problem, not much to do. If k is non-zero, and sometimes people would break that further, if k is greater than 0, k is less than 0. And then she says, okay, if it's non-zero, then we know the two aren't the same. And the part that she knows from class was we have to look at the improving directions. Okay, so she starts to get a gradient. She's going to compare those gradient. And so some of you did get that. You said, okay, with the calculus approach, I'm going to take a derivative, which is a gradient, higher dimensional space, and you compare those two, and you came to this conclusion. But here's where many of you stopped. And Jenna then went on and said, well, actually, I have to run an improving search algorithm. So she did some iterations of this. Like she actually shows what's happening for both of them. And that's what I thought was clever. This approach never would have come to me, that I could actually go ahead and do some steps in this and reach a conclusion. Yeah, and so she's doing some steps and showing that you eventually do get to the same place. Let's see, and then the conclusion, yes, then she goes back and says, none of this assumed linearity in either the constraints or the objective function. And that's exactly what you do with a proof. And many people did that. Like, hey, here's my proof. Nowhere in that proof did I say anything about linearity, nonlinear convexity. Did I mention any of those terms? So this has to work for all of those. So excellent job. And then let's see. Then the next thing, last comment I think I'll use. So, yeah, again, so mine was a proof by contradiction. Go take a look at that, because that's another proof technique that is used so often. And I just want to say how often I use proof by contradiction in some of my sort of mathematical work, I should call it. I consulted for this company, Trilogy Sailing, several years ago. And they were a giant catamaran sailing company in Hawaii. They had these huge vessels, and they would take people out on tours. And business was good, but then they decided, and they had just sandwich boards, and they would get enough tourists walking by and get people that way. But then someone came to them, a techie guy, and sold them on the fact that I'll bring you more business if you let me do this SEO, search engine optimization, for you. And so he looked at the website, made some changes, and they decided they write a contract and decided to hire him. And in this contract, somehow it was written that they could not, like he was their SEO guy in perpetuity. And if they ever tried to get rid of him, then it would be a lawsuit for millions of dollars and some percentage of the company and all this. I don't know, they signed it anyway. But now they want to get rid of him. They're 2 years into the contract, and they realize maybe he isn't bringing the business that he said he would, and his fees are pretty high. They're having to pay him like $200,000 a year for this, and it didn't seem much different than without his help. And in the contract, it had something to the extent that he was going to improve business by some percent. And then there's this great debate: did he do that? And this is what it would have been grounds. If he hadn't done that, then they could have actually terminated it, and then wouldn't have had to pay him, terminate the contract. So somehow they hire me because they know I do. I've written a book about search engine ranking, so I did some stuff about how Google works, and then Google's optimization, and I work on optimization, so that's not SEO, but they thought it might be, and so they called me. When they called me to talk about the case, just the sort of preliminary call, it was clear, even though I didn't, and I told them I'm not an SEO person, but I know a good bit, having done some websites and know some of the tricks that search engines look for and what people do. But I also told them they were complaining that it was like a trade secret that what he had done. He was hiding behind, I can't tell you what I've done. It's part of a trade secret. And I was able to immediately say, well, not really, because if you go to any HTML page in any browser, there's a way where you can view the source code. And so you can just see what he's done on your page to optimize it. You can see what sort of meta tags he put on your keywords, with the title tags, and if there's any sort of hidden, is he using Google Analytics and all this sort of stuff. So I was able to tell the lawyer that. He's like, okay, well, would you be interested in working on this? Yes, we work on an hourly rate. And the case goes on for a couple of years. And at some point, there's what's called a discovery phase in a case where our side asks for information and they have to give it to us. And they weren't giving some of it, and they were claiming they didn't have this. And what we kept asking was their what is a conversion rate. So he should have been keeping, as an SEO guy, like how many people or visitors are coming to the page, and then how many eventually get to the shopping cart and click and buy something. That's your conversion rate. And he had claimed in this case that he had doubled their conversion rate. And this would be easy to find if you're using something good, tool like Google Analytics. And for some reason at the beginning, when they transferred to him, there was a competitor to Google Analytics. I forget the name of it at this point. But for any rate, there was a period for which there didn't seem to be data on this conversion rate. No matter what we tried, our side's information that we had, their sides, and again, they claimed that didn't have it. And it actually seemed like a legitimate claim because there was some transition period in there that you didn't have it. And so our side and the lawyers and everybody, all the accountants, they kept saying, well, how are we going to show this? What are we going to do? Like, he keeps saying he's doubled it. How are we going to deal with this? Lots of thinking. I'd say, well, could we get this kind of data? And they'd ask that for the other side. No. Well, what about this? Would that be like a proxy or substitute? And then finally I came to the fact, well, if he had doubled the conversion rate, let's assume he did, and then let's see where that takes us. And this is sort of a proof by contradiction. You say, well, I don't really think you've doubled it, but let's say you did, and then let's see where it goes and see where it leads. Well, again, what we would have seen is if that were the case, then certain things would have held down the line in their figures, their accounting figures. Like we would have seen if you've doubled the conversion rate, then certain lines in their spreadsheet, and we would have seen a graph that looks, as their accounts are going like this, and yet we didn't see it. We saw something more along this line. We would have seen this kind of track. And so I was able to do a proof by contradiction and say, if this is what we would have seen, and this is what we did see. So this is the actual data. There's some discrepancy here. It must have been our assumption in the beginning. And I had to write the expert report and show these graphs and show everything and write it. And I remember the lawyers, and soon after, because there's places where you have to sort of have preliminary information with the judge, and both sides present certain parts of the case and have depositions and everything. And that was sort of the thing that made them settle, because they were like, oh, actually, this is so clear that even the jury, even someone that doesn't know math or technical stuff, can totally follow that proof by contradiction line of argumentation. And the lawyer hadn't even heard of that type of proof by contradiction, which kind of shocks me, because I thought they took a lot of logic. And so again, there's a case where these proof techniques, they kind of seem like for something you're doing for your master's degree in math, like they're a bit of a, remember there's proof by contradiction, proof by contraposition, proof, all these, the 4 or 5 classic ones that you would learn at 295. And the one that I find in my research and my consulting that I use most often is that proof by contradiction. Whereas Jenna's would have been classified as a direct proof, right? As a very straightforward one program. And this proof by contradiction is sort of a back end way of doing it. Okay, well, I babbled for too long there with storytelling at the end, but let's remember Monday's exam. Do your study with your group members, make study guides, share, discuss things. I think that's a great way to prep and look at the practice exam and practice video. Also go back over your old quizzes and your old suggested homeworks. That's the attack that I would use for studying. All right, have a good time, and we'll see you on Monday.